Okay, so this will be some simple problems in integration. So simple problems in integration, with the theme being just mean value type problems. Okay, maybe we can mention that, because last time we did some theoretical questions which are also very useful, but these will be easier, I hope. Let's see. So yeah, so let's just quick begin. There's nothing to say here. Let's begin with problem 1. So it is about taking the mean of a certain function. So f is a continuous function from a to p. We have shown that continuous functions are integrable. So this function, and we want to say that, so show there exists a c such that fc, the value of this function fc, is equal to, so I'll just write the quantity, let me not say anything first. So this will be the bridge of this. Shouldn't we take the square of the function, and then we have to take the square root of the whole thing. Yeah, that's right. Okay. Okay. So we want to show that there is a c, such that this, basically this quantity is attained by the function. Okay, at some point. So so I should mention the limit. This should be from a to b only. Yeah, a to b. This expression is going to be very useful later, or you might have seen it earlier, already. This is a very useful expression. This keeps showing up everywhere. But let's just solve this first. Yeah, so why don't you state it? You state the first, yeah, because I've not formally done anything like that. So you state the first, yeah, so MVT1 of integration, of integrals. You can say anything. I mean, you can say just it should just make sense, yeah. Into whatever it means to you, that is, it's fine. Mm-hmm. Mm-hmm. B minus A is important, right? Yeah, so I was, yeah, this times B minus A. Yes. Okay. So this is something that all of us know, right? And basically, this can be just simply proved by interpreting this as the area, right? You have to interpret the integral as the area, okay? And you just have to say that the area of the function is so if the function has a maximum and a minimum, okay? So see, this is important, okay? You need the function to have a maximum and a minimum, or rather, I think you need the function to be continuous, okay? So do you guys agree with this? Just being integrable will not give the result. Okay, you need f to be continuous also. Huh? Yes, yeah. So this should be that side. Absolutely, that's right. Yeah. Because that's a rectangle. Yeah, that's right. Yeah. So I'm just giving us just something that you guys already know, but just saying it, that f, you put f between the maximum and the minimum, then the integral from a to b is also between the maximum and the minimum. Okay. All right, and and so you are looking at a quantity in between. You're looking at this quantity t, which is between the maximum and the minimum, right? So these values are actually attained by the function. Okay. So this small m and capital M are actually attained by the function. So t should also be, or rather, t by b minus a should also be attained. Okay. So t by b minus a will be attained by the function, and so it will be equal to f of c for some c. Okay. This is just a. I should just call this a area. Okay. So basically here we just saw that there is this expression which is area, and rather you can divide this. I think that's better to divide it and say, so there is the average value of the function, and the average value will be attained by the mean value function, mean value theorem. Okay. Essentially, here is this quantity which is between the maximum and the minimum of the function. And so it is attained because of continuity. So only integrability is not will not give the result. You have to be careful there, because that's where one can get trapped, okay, in applying it in the wrong way. So okay, if there are any questions, otherwise let's solve this problem. This problem is exactly same. Okay, so the problem I've given is exactly same principle. Yeah, this is your connection okay today? I think you said something once I didn't hear very clearly. So just that's why I'm just asking again. Yeah. Mm-hmm. It's fine now, I think. Okay, okay, no problem. That's why you were saying something. I was thinking, what is he saying? Because half the things you're not was not coming. Anyways, yeah. Never mind, it's okay. That was an easy class, but still, you can see it later on. I'll upload it. So, fine, never. Let's do this problem. Yes, yes, yes. It is. It was just that. Yeah, it was just that. Uh, no, but the decimal thing was slightly. Anyways, yeah. Let's do this. So we need to just show that this quantity is also some kind of a mean. And it just looks like that. Just look at this expression, right? It looks like a mean. Mean meaning what to be my mean here? I'm trying to say that it's between the maximum and minimum of f. It just looks like that also. Okay. One can say that formally, but then it will be just giving away. Take gx equal to, and then apply the theorem. Then apply the mean value theorem. That is perfect. Yeah, just take gx equal to fx square. Adish, was that the same thing you were saying, or? Yes. Okay, then it's perfect. Yeah, but we can just say that this value is in between the maximum and the minimum, just by the. But that's just giving the proof. But okay, that just saying that if fx is between m and this, then fx square is just those values are actually attained. So I should have actually put equal to last time, and here also, and then again integrals, and then again quotient, and then so on, so on. You can just show that this quantity is again in between the maximum and the minimum. It is again a mean. Okay. So there's a phone call coming. I'll just take it. Okay. Then I'll give the next question. Sorry, I'm back. Let's move to the next question. This was easy question. Let's do slightly harder questions. Problem number 2. This one is interesting. Okay, so here we have again f is continuous. So f is continuous. So f itself is a kind of an average, is like an averaging parameter, kind of. So from 0 to 1 fx dx, this is 1. Okay, so the integral of f is 1. Okay, now let's say you're given an n, okay, we want to show, show that there exists some numbers like c1, c2 till cn, n of them obviously. And let me also maybe say, no, let me not say, I don't know actually, such that this adds up to 1. Okay, so you can achieve the area. So this is a generalization of the mean value theorem, kind of. Wait a minute. So I was thinking they should be, no, sorry. The n. Okay, so I don't know how to do this. Let's try this. Okay. Okay, so you have an idea. Okay, so just give me 30 seconds. Let me also just absorb the question. So for any n, we want to show that n can be attained by n values. Okay, so then you can tell, just maybe say the idea maybe first. Okay, so now let us just think. Okay. So I think this is a good hint. So just give us a firm time. Let's see, others should also make something out of this first. This is already good hint. They're not say. I mean, yeah, I think they will end up being distinct, but yeah, they should be. I should. Then it's not good, right? So this should, I should put that it is distinct. Otherwise, it's trivial. Right? Otherwise, you can just take the same n as same ci and. So let's see. So then you have an idea what to do from here. So after this, let's say we've split this. Yeah, so just what you said in the beginning, just apply that. Just apply the mean value theorem and you should get, right? So this will give you, the first term will give you this, yeah. And similarly, the second term will give you this, and so on and on. You will get f of cn, right? And so then what? But then this is equal to 1, we know, right? And so then we get it, right? What does it mean geometrically? Little bit. So whatever the area is in this portion, so there is this, but in this portion, whatever the area is, we don't know, but the value, because the n is coming, geometrically is not, I'm not able to see it. So there is a value here such that the such that the area of this So that is obviously not going to be the value, should be somewhere. No. Oh, first I put the point. That's wrong. No. So what I'm just trying to see, so maybe somewhere here. So yeah. So there is this point. So the area of this rectangle is the area of that thing. And similarly, they have another rectangle whose area is equal to area of that function. And similarly, we have these rectangles, and the sum of the areas of this rectangle is 1. But because you have divided it into n parts, and so that's why this n comes. I think this is an interesting result, right? That any integer n can be obtained by n parts. Yeah. Okay then. So this was simple. Yeah. I see there's a variation of this given. So let me ask that to clear this. No. So with the same conditions, we want to, so there exists, once again, there exists distinct C1, C2 till Cn, okay, such that 1 by 1 by this thing, so many things, huh? 1 by this thing is equal to n. Yeah, summation 1 by f of ci will be equal to n. This one seems more interesting. Now it's
that if this thing is the proof, then
all of them. Okay, I don't agree with am equal to hm thing, but where is the am? You mean the integral itself is the am? Oh, that way you're saying. No, but this could be different CIs, no? It is not the same CIs. You see the point. These are different. But still, maybe that we should take all the, I don't know, yeah, let me think. Yeah, this time we have to do something different. Yeah, I think I see. So any ideas? Last time we broke up the interval from 0 to 1. This time we have to break up something else. So any ideas? 1 by we want to make sense of 1 by f of ci. So like, I mean, if there is anything like ai, I don't know, ai to ai plus 1, right? And you find a ci in that which gets you that area, then let's see what we get. Dx, this is equal to f of ci times ai plus 1 minus ai. Now you have to bring this f of 1 by f of ci, right? So you have to bring the f of ci down. And then we get ai plus 1 minus ai by this thing. So now you should think like, what should you take? Like you want to be adding things to something like this. Yeah. So well, the idea then is that you would want to make this thing as simple as possible, right? The thing in the denominator. You would want to make that as simple as possible. So with that in mind, I'm thinking that we break up the area itself into equal pieces. Is that right? Yeah. So 0 to 1. So if so basically you find out, I've already used this a notation. So a1, a2. So here maybe you need a larger one, a3 and so on, so that the area of each piece is 1 by n. Yeah. So you divide the area into equal parts. Okay. Choose I should say a not equal to 0 also, but so that the area from ai to ai plus 1 is equal to 1/n of the whole area. Now you have to tell me what to do next. Yes, like now you can just add it, okay? Because if this is 1 by n, so this is obviously, yeah, this is ai plus 1. I've already written it this side, ai plus 1 minus ai times f of ci. Now you can see, you can add it. Okay, so this was the idea. Okay, so is this okay with everyone, or is there any problem? No problem. Okay, now but there is something which we have assumed here. Okay, so I mean, what makes us able to choose these ais? Rigorously speaking, how would this, I mean, why would such ais exist? That is not rigorously, we don't have that yet, right? So how do we say that? So think, then I'll try to say it in a more clear way. The question is, why will such AIs exist, which break up the area into equal parts? Because this is not the area of some circle or rectangle, so that we know. I mean, this is can be some strange function. Right. So we have to use intermediate value theorem on integrals, right? So, uh-huh. Yes. Minus T2 T2B. Okay. A different, yeah, different signs. Yeah. Okay. Yeah, that's a harder way to do it, but that's fine. That's correct. Yeah. So there is a T where this is 0, right? So there's so not T, I should just say there is a C, so that f of C is 0. And that C will really make the area half. Two equal halves. And so in this case, it will be half. Right. So, okay. So that's okay. And one can extend this idea in general to do it. That's fine. But here is a question. Why is this is might be a silly question, but why is this continuous? Let's say come 0 only. Doesn't matter. Yeah, should be 0 only for our context, but yeah. Why is this continuous? So this is a little bit of related theory that we can see maybe. And yeah, so let's answer for that only first, then we can think later for non-continuous.
Since if it's continuous, so integration
But why? Yeah. So why is it differentiable? Yeah, so that's it. So that's the thing. So let's try to prove that, right? It's not very difficult to prove, right? So why is this differentiable? Yeah, that is what it is called then. Yeah, I think. Yeah. So why is this differentiable? So let's see. This is very, very simple, but we should just see it once. This thing. And we have to just check the definitions basically. Okay, there's nothing to do. So you just do this and you have t plus h, and we can see if we need continuity of f or not. Okay. So for now we are assuming f is continuous. So then what should we do next? Yeah, right. That's regardless of, yeah, that is from t to h. Perfect. T to t plus h. Okay. Okay, you want to, okay. Yeah, you can apply that. Yes. Oh, yeah, so certainly that can be done. Yeah, but we can also do it without applying that. Okay, just for saying, huh? Which part? This part. Huh, so you can just apply the mean value theorem, right? So what he's saying is that this is, or yeah, so this thing, right? This thing is just equal to what? This is equal to f of c times h for some c. Huh. Yes, that way also, and also it is not very useful here because the c will keep changing based on the h, right? When you take the limit of h, then you'll get into some questions. So better to avoid it. Yeah. So I think there is a very simple way to do it, because you could say that you could say that fx is bounded in t to t plus h, right? So you can take max of fx in this region, and that is some m. Wait, is it working? Let's do it. So if fx is, yeah, but then yeah, the greater than is not useful. Yeah, the h will cancel out. That is a little thing. Anyways, so you get the 1 by h, and we get, okay, let me just write everything clearly. X, and this is equal to m times h, and h will cancel. So this is equal to m. So, but this doesn't give us the differentiability, right? Yeah, it doesn't give us a differentiability. It does give us continuity. You can, this is not complete proof, but you can do the other way and also show this minimum thing. And so it does give us continuity, right? But this argument so far doesn't give us differentiability. Okay. And so but one thing you can see, and this is a good thing here, that this thing is differentiable regardless of whether f is continuous or not. Sorry, this thing is continuous, at least that's what we have shown, right? Because f of t plus h minus f of t is less than hm. So as you take the limit, it will go to 0 because the m here is now fixed, yeah, in that interval. So as h becomes smaller, there's no problem. It's only better. Okay. So we have shown that regardless of anything, no, but you have to apply the squeeze theorem to show that it is continuous. You will only get that it is continuous. Huh. But yeah. Mhm. Yes, yes, yes. So for that, you may need the continuity of f. Okay, yeah. That's right. That's right. Yeah. But I'm just saying that just to see that continuity. So to show the differentiability, you may need continuity. But here the good thing is that to show the continuity of this, we don't need continuity of f. Okay. So ft is continuous. Yeah. Even if f is not continuous. F has to just be integrable in the sense that the Riemann integral should exist. Okay. For any t, that is important. Okay. Not just from 0 to 1. Okay. For any t, it should exist. Okay. uh, uh, Even if f is not continuous. So this is a good result, I feel, and this is simple, but it's what it is. Yeah. Okay. Now let us, if this is understood, then let us come to the differentiability part. So let's assume the f is small f is continuous. So then, no, but then I should not be writing this as m, right? I should let me write this as mh. Okay. So then what we are getting is by h. So this similarly things will cancel and so on, and this will become m capital mh, and this is and here maybe it should be mentioned what mh is. So yeah, this is mh. Right. So now how do we show the rest? Yeah, to show differentiability. So I think there is another mistake I have made, right? This should be not t to t plus h, but yeah, maybe it can be said, but let's be safe. We have to take t minus h to t plus h. But wait, what is happening? Yeah, okay, h can be negative also, right? Yeah, that's fine. It's okay. We are taking, yeah, we are taking t to t plus h. No. So one has to be careful. So if you take f of capital F of t plus h minus f of t, yeah, so that is, yeah, but because you don't know, yeah, we should just take t minus h to t plus h because we don't know the sign, right? Yeah. And also when you're taking the limit in differentiability, you have to consider all of them. Okay. Right. But now basically when you take the limit of this, when h tends to t, right? Limit h tends to t. Yeah. Then we will get, then are we going to get that this limit and this limit are same? Sorry. So that's, yeah, h has to go to 0. That's all. Yeah. Yeah. And that is true. That's just a definition of continuity, right? When h goes to 0, then the total, variation between t minus h to t plus h can be made epsilon for any epsilon by taking small enough h. And so, yeah. So basically, if any f of y minus f of x is less than epsilon for all y and x in this t minus h to t plus h, then it implies that the max and the min difference will also be less than epsilon, right? And so they will do the same thing. So the middle, okay, will also tend to that. So here we needed the continuity of the initial function. Without that, this capital F doesn't become differentiable. These are the subtle things in the mean value theorem, which if you just try to remember all the time, then it's not very healthy. You will keep, you'll have, yeah, I'll not be sure. But if you know how to prove it, then you're like, okay. If I forget, I'll prove it. There are very small nuances. So, okay. Okay. So yeah, so this is the two problems. We also discussed a little bit of theory. Right. The epsilon argument is not very clear, right? So let us see. Yeah, so the maximum and the minimum, and you see the difference. Okay. No, so what I'm saying is, I'm saying that there exists a h, so you can make a small enough h such that f of y minus f of x, this gap, right? This gap can be made smaller than epsilon, okay, for all y and x in the h neighborhood of t. This you agree? This is because of continuity. Yeah. So this is from continuity, right? I mean, so you can compare it with t, f of y minus t, f of x minus t, epsilon by 2, epsilon by 2 you can do. But this is what essentially you get after you add them. Yeah, so I should have said that. This is the, okay. But then this implies that this f of maximum and minimum, okay, so that is not correct. The maximum value and the minimum value in that range obviously has to also be less than epsilon because those are two values. Yeah. which are retained by the function. Some fy will give this, some fx will give this, some x fx will give small mh. So yeah, so basically this means that mh and small mh, the difference tends to 0. So they tend to the same thing, right? So this thing and this thing tend to the same thing. Okay. And where do they tend? I mean, that's also important, right? We should know that they tend to something, right? They tend to f of t. That's also clear. That's the meaning of continuity. So you need full continuity. And so because what I have written here is this limit, existence of limit at t. But existence of continuity at t is also important, right? Because then you know that this actually fy, fx, they tend to ft. So mh, small mh also tend to ft. And so this limit is not nothing but equal to ft. And that is the ftc, right? Okay. So okay. So this is the small things that we are seeing. Okay. Yeah. Yeah. So I wanted to do one more question, but today I have to just stop a little early, in fact. Okay. I'll make it up next time because I've missed my dinner. So yeah, but I will nonetheless give you the question and you can try it. Okay. I will discuss it next time. Next time will be tomorrow. Definitely we'll do a class tomorrow. I'm not sure what to do. So someone was telling me some topic. What topic was that? If you still want me to do. Otherwise, I can just continue with matrices or something. Yeah. So just say some one of them. I'll do one. Huh. Oh, okay. Though they never come in CMI ISI entrance, do they come?
They do.
They do. Okay. So I've not seen the. Okay, okay, okay. They do. Yeah. Okay. So then we should do right. So tomorrow, then tomorrow, let's do Bayes theorem then. Yeah, I think we can do that. Okay, it'll be good. So tomorrow we can do on Bayes theorem, and then after that, that gamma function and so on, I've never used them, and so yeah, I'm a little shaky with that. Okay, anyway, let me just quickly give the question so you guys can try it. Okay, because today I have to just run. So today's class is like a half class kind. We didn't really do the full class, but either ways, let's see. So there is this function f, again, it's obviously continuous, it's differentiable, and it's from a to b. Okay. So you guys can just try this immediately. Okay. Like just in the next sometime, just try it. Okay. Like don't keep it for next day. Just try this. So the derivative is bounded. Okay. And we want to say that this difference, so you take from the half. Okay. So you go till half a plus b by 2 fx dx minus this. Okay, and then the other half. Okay, this gap. Okay, so we just saw that this gap can be made 0 if you choose some property. But now if you actually choose half, okay, if you actually choose a plus b by 2, then what can you say about this gap? And it's already said here, but though this can be guessed very easily, I think. It's a geometrical interpretation. Yeah, so you just show this. So there's no existence or anything. You have to just kind of put a bound to this thing. So the derivative is important. Okay. So just try this. Okay. And so today just give me a little thing. Next time I'll make it tomorrow. We'll do a longer class on Bayes theorem. Yeah. Okay. Because I wanted to discuss the mock paper also, but I'm a little hungry. I have to do my dinner. Okay. So just note that question. And yeah, then we'll meet tomorrow. But I'll send a mail. Note it down. Huh? I don't. Yeah, you can just read because I don't know what really will come in that. Yeah, it because let me. So Rasugro, what question? Do you know a CMI question in which it came? So maybe just find that and tell me. Okay. I'll just say it in the, just tell me before because yeah. I'm a little shaky with those things. Okay. They are, I don't think they are necessary. But we'll just do, it will be fun. So we'll just do them, nah, no problem. I mean, we can, huh? Huh. So okay, Rasuguru will give us, I know a few things on Gamma, I can say. It's fine. We'll do one class on that. It'll be fun, good for me also. Yeah, and it will be good, so don't worry. I will say it in a way that, the other things you can apply it here and there. So it's fine. Don't worry. Yeah. Okay, then note this and then after noting this, you can leave. Okay. Okay. Thank you.